All right, welcome to another deep dive today. We are going to we're going to take a closer look at search.
Okay.
So much of what we do online, involves searching for things. Whether that's trying to find a contact in your phone, or looking for just the right video on YouTube or whatever it is.
Yeah.
So, you sent over some really interesting material that dives into the actual algorithms, the actual like computer science behind how search works.
Yeah, it's really interesting stuff, like kind of behind the scenes stuff that we don't think about too much, but it's like, these algorithms, they're kind of the unsung heroes of the internet. Like, I
Yeah.
mean, can you imagine if we didn't have good search algorithms? Like everything would just like slow to a crawl.
Yeah, it'd be like the early days of the internet all over again.
Totally,
Yeah.
totally. Yeah.
Yeah.
So yeah, the stuff you said over it focuses on a couple of the main algorithms,
Okay.
which are like the most fundamental approaches to search, which are linear search and binary search.
Okay, and those are the two that we're going to kind of unpack in this deep dive.
Exactly, yeah.
Okay, so let's start with linear search.
Okay.
Can you give us kind of a high level overview of what that is, how that works?
Yeah, absolutely. So linear search, I mean, it's really straightforward. Basically, you go through each item in a list
Mm,
one by one until you find what you're looking for. It's kind of like, imagine you have a shelf full of books and they're not in any particular order,
right.
and you're looking for one specific book. So you just start at one end of the shelf and you check each book one at a time until you find the one you want.
Yep.
And that's pretty much it. I mean, there's not really, any more to it than that. It's like super simple.
Yeah, it's a very brute force approach, right? Yeah.
Exactly, exactly. Like it doesn't really require like any, any special organization of the data or anything like that. Like even if your books were like totally jumbled up on the shelf,
Mm.
like linear search would still work. This might take a while if if your bookshelf was really big.
Right, right. So the materials that you sent over, I mean, it sounds like there's one in particular, a YouTube video called "Algorithms and Data Structures Tutorial."
Oh, yes. Yeah, yeah. That one, yeah.
And that one kind of explained linear search using that same analogy of going through a list, like item by item, comparing each one to what you're trying to find, to the target, as they call it.
Right, right. Yeah, exactly. They like break it down step by step, which is actually, pretty helpful, I think.
Yeah, definitely. And so when it finds the book or when it finds the target value, what exactly does it return, like as its output? What information do we get from a linear search?
So when linear search finds what you're looking for, it tells you the position of that item in the list, like its index.
Okay.
So like if your book was the third book on the shelf, it would return like the number 3, or like index 2 if we're talking about like zero-based indexing like in computer science.
Yeah.
But, and then if it goes through the entire list and it doesn't find it, then it just basically tells you like, hey, it's not there.
Okay.
So yeah, it's
Yeah.
pretty straightforward.
Okay, so it's a pretty simple method, right? But it sounds like, if you have a really, really long list, like a huge data set, it could potentially be pretty inefficient.
Yeah, yeah, exactly. I mean, that's the main drawback of linear search is that if your list is really big, then it can take a really long time to find what you're looking for,
Okay.
especially if, what you're looking for happens to be like at the very end of the list or something like that.
Right, right. So it's fine for small data sets, but for really big ones, that's where binary search comes in, right?
Exactly. Yeah, that's where binary search kind of comes to the rescue.
Yeah.
And that's a much more efficient algorithm.
Okay.
But um, it does have a requirement.
Okay.
Your data needs to be sorted for binary search to work.
Okay, so it can't be a jumbled up bookshelf anymore.
Exactly. Yeah. It needs to be like in alphabetical order or numerical order or something
Yeah.
like that,
Got it.
so that the algorithm can like actually do its thing.
Okay, so how does it work? What's the basic idea behind binary search?
So the basic idea is to like keep dividing the search space in half,
Okay.
right? So like instead of going through the list one by one, you start by looking at the middle element
Okay.
and you compare that middle element to what you're searching for.
Okay.
And then depending on whether the middle element is greater than or less than what you're looking for, you can eliminate half of the list right away. And then you just repeat that process with the remaining half of the list.
Got it.
And you keep doing that, keep dividing the list in half until you find what you're looking for.
Okay, that makes sense. And I think the YouTube video you sent over used a really good analogy to kind of explain this, right? It was like someone trying to guess a number.
Yeah, yeah, I remember that.
Yeah, and instead of guessing randomly or going through numbers one by one, they would always guess the middle number.
Right. Yeah, exactly. And then, like, based on the feedback, whether the guess was too high or too low, they would then eliminate half of the remaining numbers and keep going,
Right.
which is exactly what binary search does.
Exactly. Okay, so binary search also aims to find the location, the index of the target value
Yes. Yeah, that's right.
within the list, but it relies on this really clever, divide and conquer strategy.
Exactly. Exactly.
And so, just to be clear, it has to be a sorted list for this to work.
It absolutely has to be sorted.
Yeah.
Like, if it's not sorted, then you're going to get, like, totally wrong answers.
Got it.
Like, the algorithm, it relies on that order to be able to eliminate half of the list at each step.
Okay.
So yeah, that's a really important point.
All right. So we've got linear search, which is simple but can be slow for big lists.
Right.
And we've got binary search, which is much more efficient but requires the data to be sorted first.
Exactly. Yeah.
Okay.
That's a good summary.
Okay, so the materials also mention this thing called big O notation,
Ah, yes, big O notation.
which sounds kind of, like intimidating.
Yeah, it sounds a bit scary, but it's not that bad once you kind of wrap your head around it.
Okay, so what is big O notation?
So it's basically a way to, like, talk about the efficiency of an algorithm,
Okay.
right? Like how the performance of the algorithm changes as the size of the data grows. So, like, if you have a small data set, then, most algorithms are going to be pretty fast. But, as your data set gets bigger and bigger, then the differences between different algorithms can become, like, really significant.
Okay.
And so big O notation is just a way to, like, express that relationship, between the size of the data and the time it takes for the algorithm to run.
Okay, and so how would we describe the efficiency of linear search using big O notation?
So for linear search, in the worst case scenario, you might have to look at every single item in the list,
Right.
right? Like if what you're looking for happens to be the very last item in the list.
Okay.
So if there are n items in the list, you might have to do n comparisons. So we say that linear search has a time complexity of O(n).
O(n). Okay, so the time it takes grows linearly with the size of the list.
Exactly, yeah.
Yeah,
So if you double the size of the list, you double the amount of time it takes to search.
Okay, that makes sense. And the Python code example in the video actually showed this really clearly, right? It was a for loop
Yeah, right.
that could potentially go through every single item in the list.
Yeah, exactly. Exactly. Just like iterates through the list one by one.
Got it. Okay, so how about binary search? How does that compare in terms of big O notation?
So binary search is much, much more efficient because, like, remember how we talked about how it keeps dividing the list in half?
Right.
So the number of comparisons it needs to do grows much more slowly than linear search.
Okay.
In fact, it grows logarithmically. So we say that binary search has a time complexity of O log n.
Oh, log n. So it's logarithmic. Okay, and that's a lot better than linear, right?
That's way better, yeah. Especially for large data sets.
Okay.
Like, to give you an idea, if you have 1 million items in a list, linear search might take 1 million steps in the worst case. But binary search would only take, like, around 20 steps.
Wow, that's a huge difference.
Yeah, it's a really big difference.
Okay, so binary search is clearly a lot more efficient for large data sets.
Yeah, absolutely.
But you mentioned earlier that it requires the data to be sorted.
Right. Yeah, that's the key requirement.
What happens if you try to use binary search on a list that's not sorted?
You're going to get, like, totally wrong answers.
Okay.
Like the algorithm, it just won't work correctly. It's designed to work on sorted data. And if the data is not sorted, then it's going to get confused.
Got it.
Yeah, and, like, the video actually, like, they even gave an example of this.
Okay.
Like where binary search on an unsorted list might incorrectly tell you that a value isn't in the list when it actually is.
Okay, so it's not just that it's less efficient, it's actually inaccurate if the data is not sorted.
Exactly, yeah. You can't trust the results if you use binary search on unsorted data.
Got it. Okay, so let's walk through the steps of the binary search algorithm, like how it actually works.
Okay, yeah, sure.
Yeah.
So first you find the middle element of the list.
Okay.
And then you compare that middle element to the target value, to what you're looking for.
Okay.
If they're the same, then you're done. You
Yeah.
found it,
Right.
you know. and the algorithm returns the index of that middle element.
Okay.
But if they're not the same, then you have to decide whether to look in the left half of the list or the right half of the list.
Okay.
And you do that by comparing the middle element to the target value.
Okay.
So if the middle element is smaller than the target value, then you know that if the target value exists in the list at all, it has to be in the right half of the list.
Right, because the list is sorted.
Exactly, yeah.
Yeah.
So then you just repeat the whole process with the right half of the list.
Okay.
And you keep doing that until you either find the target value or you've narrowed it down to a single element that's not the target value.
Okay, and if you narrow it down to a single element that's not the target value, then you know it's not in the list at all.
Exactly, yeah.
Okay, so it's basically like, repeatedly cutting the list in half until you find what you're looking for or you run out of places to look.
Exactly, yeah, that's a great way to put it.
Okay, so the video also showed some actual Python code for both linear and binary search.
Yeah. Yeah, they did.
Were there any key things that we should take away from looking at those implementations?
Yeah, I mean, the code for linear search, it was pretty straightforward,
Okay.
It just used a for loop to iterate through the list and compare each element to the target value.
Great, right.
And, that really highlights like that ON complexity,
Okay.
like the fact that the loop might have to go through every single item in the list.
Okay.
And then the binary search code, they showed a couple of different implementations. One was iterative
Okay.
and one was recursive.
Okay.
And so the iterative version, it used a while loop and it kept track of the first and last indices of the search space.
Okay.
And then it would like keep updating those indices as it narrowed down the search space.
Okay.
And it used those conditional statements like if else statements to like compare the middle element to the target value and decide which half of the list to look at next.
Okay, and so what about the recursive implementation? What was that like?
So the recursive implementation is a bit more concise, I guess you could say.
Okay.
But it basically, like the function called itself over and over again with smaller and smaller sublists
Okay.
until it either found the target value or it hit the base case.
Okay, and what was the base case in this particular implementation?
So the base case was when the list was empty.
Okay.
So like if the function got called with an empty list, then it would immediately return false because, the target value obviously can't be in an empty list.
Right.
And that would stop the recursion.
Okay, so the base case is basically the condition that tells the function to stop calling itself.
Exactly. So,
Yeah. Otherwise, it would just keep calling itself forever and ever.
right. Exactly.
Okay, and so so the video also briefly mentioned this idea of space complexity.
Ah, yes. Space complexity.
Which is about how much memory an algorithm uses.
Right. Exactly. So like time complexity is about how long it takes to run.
Right.
Space complexity is about how much like extra memory it needs.
Okay.
So like you can think of it as like how much scratch paper the algorithm needs to do its work.
Got it.
And so they contrasted the iterative and recursive implementations of binary search in terms of space complexity.
Okay, so how do they compare?
So the iterative version, it uses a constant amount of extra memory,
Okay.
no matter how big the list is.
Okay.
Because it's basically just like updating a couple of variables, like the first and last indices.
Right.
So we say that it has a space complexity of 01.
Oh, one. Okay.
Yeah.
So it uses the same amount of memory whether the list has 10 items or 1,000,000 items.
Exactly, yeah.
Okay, and how about the recursive version?
So the recursive version, it uses a bit more memory.
Okay.
Because each time the function calls itself, it creates a new stack frame,
Okay.
which is like a chunk of memory that stores the function's local variables and stuff like that.
Got it.
And so the depth of the recursion, like the number of times the function calls itself, grows logarithmically with the size of the list.
Okay.
So we say that the recursive version has a space complexity of O log n.
Well, look at it.
Yeah.
Okay, so it uses more memory as the list gets bigger, but it still grows pretty slowly.
Right, yeah, exactly.
Okay, and the video also mentioned that Python actually prefers iterative solutions over recursive solutions.
Yeah, that's right.
Why is that?
So there are a couple of reasons for that.
Okay.
One is that Python has a limit on how many times a function can call itself recursively.
Okay.
It's like to prevent stack overflow errors,
Okay.
which is when you run out of memory for the call stack.
Got it.
And the other reason is that Python doesn't have tail call optimization. which is a feature that some programming languages have that can make recursion more memory efficient.
Oh, okay.
So yeah, for those reasons, it's generally better to use iterative solutions in Python whenever possible.
Okay, that makes sense. All right, so we've really gone deep into the world of linear and binary search.
Yeah, we have.
We've learned about the mechanics, how they actually work. We've
Mhm.
learned about their time complexity, how their speed compares.
Right.
We've learned about their space complexity, how much memory they use.
Right.
And we've also learned about the importance of sorted data for binary search.
Absolutely. Yeah, that's a key takeaway.
Okay, so just to summarize the key takeaways.
Okay.
Linear search, it's simple, it works on unsorted data, but it can be really slow for large lists.
Right.
And it has a time complexity of OLA.
Yeah.
Binary search is much, much faster for large sorted lists,
Right.
but it does require that the data be sorted beforehand.
Yeah, it has to be sorted.
And it has a time complexity of O log n.
Exactly.
Okay, and then we also learned about big O notation, which is this really useful way of talking about the efficiency of algorithms.
Yeah, it's a great tool for analyzing algorithms and comparing different algorithms.
Yeah, definitely. And we also saw how binary search can be implemented in two different ways,
Right.
iteratively and recursively,
Yeah.
and how they have different space complexities.
Exactly. Yeah.
So much to think about in the world of search algorithms.
Yeah, it's really interesting stuff, and like it's amazing how much these algorithms impact our lives. You know, like
Yeah.
every time we search for something online, we're benefiting from all this cleverness that computer scientists come up with over the years.
Yeah, absolutely. And so, just as a final thought for our listeners, given that binary search is so much more efficient for large data sets, what are the implications of making sure that data is sorted?
Mm, that's a good question.
Is it always worth it to sort data before searching it?
Well, I mean, it depends, right? Like if you're only going to search the data once, then it might not be worth the effort to sort it first.
Right.
Because sorting itself can take some time.
Right.
But if you're going to search the data multiple times, then it's almost always going to be worth it to sort it first.
Okay.
Because the savings in search time are going to outweigh the cost of sorting.
Got it.
And it also depends on the size of the data.
Okay.
Like if you have a really small data set, then it probably doesn't matter too much whether you sort it or not.
Right.
Because linear search is going to be pretty fast anyway.
Right.
But if you have a really large data set, then sorting can make a huge difference.
Okay. That makes sense. So there's no easy answer. It depends on the context.
Exactly, yeah. It's a trade-off,
Yeah.
You have to weigh the cost of sorting against the benefit of faster searching.
Right. Right. Well, this has been a really fascinating deep dive.
Yeah, it has.
Thanks so much for sharing your expertise with us.
Oh, my pleasure. Thanks for having me.
And to our listeners, thanks for joining us on another deep dive.
See you next time.
We'll see you next time.